If your stock portfolio loses 50% on Tuesday and then gains 50% on Wednesday, how much money did you lose?
Most people would say zero, right?
Exactly.
Right.
If your brain immediately answered, "Oh, I broke even," well, your brain is lying to you. And today, we're going to show you exactly how.
Yeah, it's a massive blind spot for human intuition.
Because, you are constantly bombarded with numbers and headlines, corporate reports, political polls,
Hmm?
and they feel concrete. They feel objective.
Right. Numbers feel like facts.
But the way data is mathematically framed, like before it ever reaches your screen, can completely alter your perception of reality. So our mission today is to act as your shortcut. We want you to be truly well-informed about the hidden mechanics of data presentation.
Which is so crucial right now.
It really is. We're doing a deep dive into some fascinating source material on the underlying math of relative change. We're exploring why absolute numbers deceive you, the specific vocabulary used to manipulate percentages,
Yeah.
and the mathematical workarounds professionals use to find the actual truth.
It's a profound shift in perspective, really. Once you learn to read the mechanical structure of the math rather than just, the surface level numbers, you start seeing these subtle framing choices everywhere.
Everywhere.
And the illusion usually starts simply because our human brains naturally default to absolute numbers. We just prefer raw counts.
Okay, let's unpack this. Because to really understand how we get tricked, we need a functional way to think about it.
I agree. Visuals help a lot here.
Right. So think of an absolute number like saying a car costs $50,000 as a photograph of a mountain. It shows you the object, sure, but relative change is the scale on a map of that same mountain.
Oh, that's a great way to frame it.
Without the scale, you have absolutely no idea if you're looking at a tiny hill or Mount Everest. I mean, the photograph gives you the what, but the scale gives you the context.
Exactly. And the problem with relying solely on the photograph, the absolute change, is that it leaves you highly susceptible to the unit illusion.
The unit illusion.
Yeah. Absolute change is just taking a new value and subtracting the reference value. But the unit you choose to measure that change in completely dictates how your brain reacts.
Right, because units feel arbitrary sometimes.
They do. If you measure the difference between a 2-meter piece of wood and a 1-meter piece of wood, the absolute difference is just 1.
A difference of 1 meter. It sounds completely manageable.
But if we measure that exact same physical distance in centimeters, you are now subtracting 100 centimeters from 200 centimeters.
Oh, wow.
Right. The absolute difference is 100. Mechanically, the physical reality in space is identical.
But the number 100 triggers a significantly larger cognitive reaction than the number 1.
Exactly. It feels like a bigger gap simply because of the unit chosen.
And relative change neutralizes that illusion by mathematically stripping away the units entirely. You take that actual change and divide it by your reference value.
Precisely. It levels the playing field.
So a change of 1 meter divided by the starting 1 meter is 1. And a change of 100 centimeters divided by the starting 100 centimeters is also 1.
Right. It yields a 100% increase either way. You get a pure unitless number that represents the actual proportion of the shift. If we connect this to the bigger picture, relative change is the great equalizer. It judges the underlying importance of a change rather than just the raw amount.
Give me a real-world example of that.
Well, if an item costs $50 and the price goes up by an absolute value of $100 to a total of $150, that item just tripled in cost.
Yeah, the relative change is massive. That hurts your wallet.
But if you are buying a $10,000 piece of industrial equipment and the price goes up by that same absolute $100.
The relative change is minuscule.
Exactly. The absolute $100 bill is physically identical, but the mathematical importance of that bill changes depending on the reference value.
I follow the logic, but I'm going to push back slightly here. Is absolute change strictly a trap, or is there a functional utility to it?
Oh, there's definitely utility.
Because if I think about my own paycheck, if my boss tells me I'm getting a $100 bonus this week, I care deeply about that absolute $100.
Of course you do.
That is real utility. I can buy groceries with that. Even if I calculate the relative change to my total annual salary and realize it's a fraction of a percent, the relative math doesn't diminish the absolute utility of the cash in my pocket.
And that's a vital distinction, really. Absolute numbers are completely necessary when the real-world utility of the unit matters to you directly. A dollar has a fixed purchasing power regardless of your total salary.
Right.
The mathematical trap only springs when you are attempting to compare two different scenarios, or, and this is key, when a narrator is attempting to frame a change as inherently massive or insignificant.
So when someone is trying to sell you a narrative,
Yes, that is when relying on the absolute number leaves your perception highly vulnerable to manipulation.
and if relative change is how we judge the importance of a comparison, percentages are the vocabulary we use to communicate it. But that vocabulary is incredibly fragile, isn't it?
Fragile is the perfect word for it. It breaks so easily.
Take the example of two vehicles from our source material. Let's say car M costs $50,000 and car L costs $40,000.
Depending entirely on which car you anchor as your reference value, the grammatical phrasing of the comparison dictates a completely different mathematical reality.
Walk me through that.
Well, if car L is the reference, the absolute difference is $10,000. You divide 10,000 by car L's price of 40,000 and you get 0.25.
So you would say car M is 25% more than car L.
Right. Or if you express it as a direct ratio rather than a difference, car M is 125% of the cost of car L.
Oh, I see. The specific words more than versus of signal whether you are citing the relative difference or the total ratio.
Exactly. The grammar literally dictates the math.
But if you flip the anchor, the math changes completely. Like if we start with car M at $50,000 as the reference, the difference is now negative $10,000.
Which changes everything.
Right. Divide that by 50,000 and you get negative 0.20. So suddenly, car L is 20% less than car M, or 80% of what car M costs.
Yes. The physical prices of the car is never moved.
Yet you can truthfully report the gap as either 25% or 20%, purely based on which bumper you decided to point at first.
It really requires hypervigilance from the listener. I mean, if you aren't paying attention to the specific noun acting as the baseline, your brain will misinterpret the scale of the math.
Here's where it gets really interesting, though. The ultimate manipulation of this vocabulary is the percentages of percentages trap.
Oh, this one drives mathematicians crazy.
We see this constantly with interest rates. Let's say a bank raises the interest rate on a mortgage from 3% to 4%. The bank sends out a notice saying, "We have implemented a 1% increase in your rate."
And that phrasing is fundamentally incorrect.
You're completely wrong. Yeah.
It is a conflation of absolute and relative terms. The absolute change between 3% and 4% is 1 percentage point.
Right. A point, not a percent.
Exactly. But to find the relative change, you must take that 1 point absolute difference and divide it by the original reference value of 3%.
Which means the actual relative change to your interest rate is 33 1/3%.
Yes.
Your interest burden didn't go up by 1%, it went up by 1/3. It's difficult not to assume that marketers and financial institutions intentionally exploit the public's misunderstanding of a percentage point versus a percent increase.
It's a very convenient confusion for them.
Calling a massive 33% spike in borrowing costs a 1% increase. Just brilliantly downplays the bad news.
When the underlying variable you are measuring is already formatted as a percentage, the linguistic waters become very muddy.
Muddy and expensive.
Very true. It requires strict discipline to separate absolute percentage points from relative percentage change. Otherwise, the magnitude of the shift is completely obscured.
So the language of relative change is easily weaponized. But the actual formula for relative change has its own mechanical failures, doesn't it? There are situations where taking the new value, subtracting the old value, and dividing by the old value just mathematically breaks down.
It does. The most obvious failure is when your reference value is 0. You cannot divide by 0. The function is undefined.
Just a classic math error.
Right. But the far more counterintuitive failure occurs when your reference value is negative. The denominator sign completely corrupts the logic of the result.
Let's use temperature to visualize this.
Yeah.
Imagine the weather outside goes from negative 10 degrees to negative 6 degrees. The temperature got warmer. It increased by a positive 4 degrees.
But if we plug those numbers into the standard relative change formula, we take the actual change, which is positive 4, and we divide it by the reference value, which is negative 10.
Okay, so positive 4 divided by negative 10.
Which yields negative 0.4.
So the formula outputs a relative change of negative 40%. It's telling me the temperature decreased by 40%, even though I know definitively that the absolute temperature increased.
Yes. The math is outputting a direct contradiction to physical reality.
That is wild.
The classic formula simply doesn't know how to handle the crossing of the negative threshold. It yields a negative relative change for a positive absolute increase.
So how do people fix that?
Well, to bypass this mechanical flaw, professionals use a special variation called percent error. It's heavily utilized in scientific fields when comparing an experimental value, like a measurement taken in a lab, to a theoretical or widely accepted value.
I like to visualize this using a dartboard. Treat the theoretical accepted value like the bullseye. The standard formula for percent error puts absolute value brackets around the top part of the fraction.
Right. It forces the numerator to be positive.
So if you throw a dart, that standard formula just measures the pure magnitude of your miss. It tells you that you missed the bullseye by 2 inches, but it strips away the context of where the dart landed.
What's fascinating here is that scientists will frequently and intentionally remove those absolute value brackets
Why?
because the negative or positive sign of the error holds vital physical context. The directionality matters just as much as the magnitude.
Right, because if you take the brackets away, the math tells you whether you overthrew or underthrew the dart. And there's a brilliant example in the sources regarding the speed of light.
Oh, yes. That's a perfect illustration.
If a physicist measures the speed of light in a vacuum, and they calculate a negative percent error without the brackets, it simply means their experimental velocity was slower than the accepted speed of light. The dart landed short. They just need to recalibrate their lasers.
But if they calculate a positive percent error without those brackets,
Then the dart went straight through the backboard.
exactly.
A positive percent error means they recorded a speed faster than light. They just mathematically violated the theory of relativity.
Which is huge.
That isn't a measurement error you just file away in a drawer. That is data that rewrites the laws of physics. The presence or absence of that single negative sign completely alters the interpretation of the data.
And this raises an important question about the rigidity of these formulas. In percent error, you must adhere to a strict operational order. It has to be experimental value minus theoretical value.
The order matters.
Yes, the values do not commute. If you flip them, the sign flips, and a scientist might mistakenly believe they broke relativity when in reality they simply subtracted in the wrong direction.
Which introduces a massive mechanical headache for systems that rely on automated math.
Oh, a nightmare for programmers.
Right. If the basic formula explodes when it hits 0 and outputs contradictions on negative numbers, how do software programmers or economists stabilize their models? They can't have a global financial model crash just because a localized metric dropped below 0.
They stabilize it by fundamentally reinventing the denominator. You see, the core mechanical flaw with the classic relative change formula is that it lacks symmetry.
Symmetry.
Standard division inherently anchors to the past, the starting reference value.
Let's walk through why that asymmetry happens. If a stock goes from $100 up to $125, the absolute change is $25.
Yeah.
We divide that by the starting anchor of 100, which gives us a 25% increase.
But if that same stock drops from 125 back down to 100, the absolute change is negative $25.
Okay, sure.
However, your anchor has now shifted. You are now dividing that negative 25 by 125, which yields a 20% decrease.
The journey is physically identical in distance, but because the denominator changed, the relative math is totally skewed. Going up is 25%, coming down is 20%. It feels mathematically unbalanced.
It is, and in data science, that lack of balance creates compounding errors over time. A relative change from state A to state B inherently must have the exact same magnitude as moving from state B back to state A.
So how do they force this symmetry?
Experts use indicators of relative change. Instead of dividing by the starting reference value, they replace the denominator with a mean, an average of the two numbers.
Wait, so if I use the average of the two numbers as the denominator, the math stabilizes.
Let's test it on the stock.
Okay, the mean of 100 and 125 is 112.5. So if the stock goes up, we divide the positive $25 change by 112.5, which is about 22.2%.
And if the stock goes down, you divide the negative $25 change by that exact same mean of 112.5, yielding negative 22.2%.
The symmetry is perfectly restored. Whether you're moving forward or backward, the denominator acts as a fixed anchor midway between the two states.
Exactly. But mathematicians don't just use a simple average. They tailor the type of mean to the specific vulnerabilities of their field.
Like what?
For instance, programmers checking floating point values in computer code are heavily advised to use maximum mean change.
Floating point values are essentially decimal calculations in software, right? Why do they specifically need the maximum mean?
Because computers struggle with dividing by incredibly tiny numbers. If a programmer uses a standard average and the numbers are close to zero, the resulting fraction could become massively inflated.
which causes a crash.
Right, a floating point overflow. By forcing the denominator to be the larger of the two numbers being compared, they guarantee the denominator is as robust as possible, mathematically minimizing the resulting fraction and keeping the software stable.
That is incredibly clever. They are choosing a mathematical flavor that actively defends against the hardware's weakness. And economists do the exact opposite, right? They use minimum mean change.
Yes, economists modeling massive financial systems will often use the smaller of the two numbers as their denominator. Dividing by the minimum value yields the largest possible relative change.
So it exaggerates the shift.
In econometrics, this acts as a built-in stress test. It forces the economic model to react to the most volatile possible interpretation of the data, ensuring the system can survive extreme variance.
It's fascinating how the specific denominator is chosen not just for accuracy, but for survival. But, averaging the denominator is still essentially just patching a broken system. If we want a mathematical framework that is fundamentally unbroken from the ground up, we have to abandon standard percentages entirely. We have to change the scale.
Which brings us to logarithmic change. It is arguably the most elegant solution in mathematics for tracking relative proportion over time.
So what does this all mean? Let's break down the mechanics. Logarithmic change uses the natural logarithm of the ratio of the two numbers. Scientists scale this result by 100 to create units called log points, or centimers.
The brilliance of log points is that for very small fluctuations, they are virtually indistinguishable from standard percentages. A 1% increase in a standard formula translates to roughly 0.995 centimers.
So to the layperson, the day-to-day numbers look identical.
Exactly. But log points possess a mathematical superpower that standard percentages lack: true additivity.
And to understand why additivity matters, we have to resolve the trap I mentioned at the very beginning of this deep dive, the 50% trap.
Ah, yes. Standard percentages are inherently multiplicative, but they masquerade as additive. This is why the human brain gets wiped out by volatility.
Let's run the math on the casual investor. You put $100 into a stock, it goes up 50%, you now have $150.
Pretty straightforward.
Then the next day, the market corrects and your stock drops 50%. Your brain naturally adds plus 50 and minus 50 and assumes you're back at zero.
You assume you still have your original $100.
But a 50% drop on $150 is $75. You are left with $75. You just lost a quarter of your entire portfolio, even though the headline percentages were equal and opposite.
Standard percentages simply cannot be added together over time. A 50% loss actually requires a 100% gain just to break even.
But log points mechanically translate multiplicative relationships, like scaling a portfolio up and down, onto a genuinely additive scale. They calculate the continuous area of change.
Which means if we map that exact same stock market journey using logarithmic change,
If your stock gains 50 centimers and then loses 50 centimers, well, you can literally just sum them up. Plus 50 minus 50 equals 0. You are left with exactly $100.
log points allow you to perfectly sum up a series of volatile changes over time without the math wildly skewing as you move up and down the scale. It completely neutralizes the 50% trap.
It's so clean.
It really is. Log change is the unique two-variable function that is both perfectly additive and matches relative change linearly. It removes the illusion of volatility and provides a stable baseline for complex systems.
So you now possess the ultimate decoder ring for the data you encounter every day. You understand the mechanics of the unit illusion and why 100 centimeters feels scarier than 1 meter.
And you know how to parse the vocabulary of deception, separating absolute percentage points from relative percent increases.
You've seen how mean denominators force symmetry in computer models and how the additivity of log points saves you from the stock market's 50% trap.
And this raises an important question for you to take forward. The next time you see a news headline declaring a massive percentage drop in a market or a huge swing in a political poll, stop and check the math.
Always check the math.
What was the reference value? Is the narrator using a specific unit or a shifted denominator to artificially inflate the scale of the change? Look past the math they want you to see and calculate the math that actually matters.
Remember the mountain. Don't just stare at the photograph and let the raw numbers induce panic. Find the scale on the map. Find your reference value. Thank you for joining us on this custom-tailored deep dive. Keep questioning the numbers around you, and we'll catch you next time.